My goodness, name something that the Indian country hasn't done. The brain power here is just staggering. You could wake up one day and find out the world's upside down. So customers are going, where else can I go? The answer is India, India, India. Either be a zero or a hero. It's one letter difference. Is this going to be easy? Absolutely not. Is it doable? Absolutely yes.
This is The Sketch, your favorite business podcast, which we are now bringing to you on video, so that when you're doom scrolling on YouTube, you can watch the business insights from our guests. I'm Sruthijith, your host. I'm the Editor-in-Chief of Mint. In today's episode, we're going to talk about microchips and semiconductors. How these tiny things are the beating heart of modern life, powering everything around us, from cars to planes to nuclear power plants. To my mind, making microchips is among the most complex things that mankind does. Everything is unfathomably tiny. The width of a strand of human hair is 100,000 nanometers. The size of the transistors on the kind of chips on your iPhone, for instance, is 7 nanometers. And they're now printing 2 billion such transistors on a chip the size of our fingernails. In the post-COVID world, semiconductors have also acquired a geopolitical dimension. India is keen to get semiconductor chips made in India and has committed subsidies of $10 billion and more to attract manufacturing to India. These are incredibly complex to manufacture. While the transistors might be invisible to the human eye, making them need mega factories, large land parcels, and mammoth investments. To speak with us about all of this today with me is David Reed, CEO of Vedanta-Foxconn Semiconductors. David is a veteran of the semiconductor industry, a German-American who has worked in the chips business around the world, and an avid hiker and a collector of Toyota Land Cruisers of a very specific vintage. David, thanks for joining us today and welcome to The Sketch.
Thank you for inviting me, and I'm very excited to be here with you and your audience. And now I'm full-time in India. It's a pleasure to be here.
You're a person of great interest. The semiconductor project, or this idea that India is going to set up fabs and make these semiconductor chips, has attracted a lot of skepticism. You are sort of this person with a lot of experience and having actually made these things, worked in these giga factories, who has landed here and is about to embark on this crazy project. I say crazy because of how wildly ambitious it is and what the kind of hurdles that are before it. What are your first impressions of this country and of this project?
This is India's moment, and I would truly believe India is in the right place at the right time with the right idea, with the right drive. And India is well known for its intelligence, its drive, its ambition. India, if you go to any company that's in semiconductor, end users, you ask the question, where is your work done? And they mention the same cities in India, the IP, the IT, the system software. So this is a very unique moment for India because there's a lot of brain power already here working on electronics and semiconductor, but what is missing is the engine. And that engine is the ability to make a semiconductor wafer where it's designed here, manufactured here, tested here, packaged here. So you might think of it as a closed-loop, turnkey, made-in-India semiconductor.
So the wafer, which is the foundation of a microchip, and the silicon wafer, is that the foundational block of this industry?
It's one of many things. Think of a wafer as it's 300 millimeters across, and that's an industry.
That's what, the size of a fingernail broadly?
No, sir. That's about 300 millimeters is the wafer is like a large platter, a dinner platter.
Right.
Okay.
Right.
And this wafer is cut very thin. And the wafer is what you manufacture the chips on. And a typical wafer can have anything from, if you have one of these very large system on a chip type chips, you may have 2,000 to 3,000 on a wafer. Some companies have 40 to 80,000 chips on a wafer, the same wafer. And this wafer is the substrate that is the basis of all the engineering, the chemistry, the physics, the light, the intellectual property is built on that wafer. Once you manufacture the wafer, you use a laser and you scribe it. Just cut it up like a chocolate bar.
Right.
And you take each one of those and you test them, and then you wrap it in a package so it can be protected, and that goes on a circuit board, and then that goes into your phone or your iPad or your TV.
So the laser that cuts it, at what point are the circuits sort of drawn on this chip and the transistors integrated?
So these circuits, a transistor, and I'm not going to go through Moore's law, or we'll be here all day, but a typical transistor, think of it this way, the latest bleeding edge transistors are probably the width of your DNA in your cell. And the mainstream transistors are probably the width or half the width of a red blood cell in your blood. That's just one transistor. And a chip can have anywhere from several billion to the sky's the limit, depending on 3D stacking, 2D layouts. So I won't say it's infinite, but you could have 20, 30 billion transistors on a chip. And the more transistors you have on a chip, the more ability that chip can do things in different conditions, different states, different applications.
So when you say a chip is, say, 7 nanometer chip, what you're actually referring to is the size of the transistors on it.
Yes, sir.
Or rather, the width of the transistor.
The width of the transistor. And think of a transistor, and there's two types of chips. There's analog, which the signal controls on and off, and then there is digital. And it's either on or off, a 0 or a 1.
Right.
And so the chips we're talking about here are digital. They're 0 or 1. And then once you print that transistor, you can control it and turn it on or off. And what does that mean? Is think of like a water hose, and it's running water, and you turn the faucet off, the transistor's off. You twist it on, the transistor's on. So that 0 or 1 sends a signal to the next series of transistors, and so you have a logic of instructions on that chip. And then the chip is run by software called firmware. And you and I don't see that, but that's sort of like, think of a city and the city blocks, and all the intersections are controlled by signal lights on and off. And you have this signal going around the chip, and you have different lights coming on and off. Think of it that way, like a little miniature city. And depending on what the instruction set is, it's either telling you something, it's either crunching numbers for you, or even it's storing numbers for you, like a memory chip.
So the logic of a chip is actually printed into it at the time of manufacturing itself?
Yes, sir. And a typical chip, so for the audience, think of if you were to pull out a map of a city, okay, and you look at this map. If you were to look at a microchip, it would look like that map of a city. You have all these blocks. This block does division. This block does multiplication. This block does something special. This block stores memory. This block controls the other blocks. And so you look at that, and depending on the application of the chip, you may want to move a lot of transistors, or you may want to move a few transistors, and this gets into the voltage. How do you move all that? And so what we do, this chip starts off with the silicon, and you have a series of steps that are repetitive over and over and over. And some, you do that step maybe 40 to 50 times. Some chips do that 300 or 400 times, all on the same wafer. And so back to my analogy of the city, you're stacking layers on top of each other, 1 through 600 steps, and each step is different. And you're going to print it with lithography. You're going to etch it with electrons to remove the material. You're going to clean it with ultra-pure water. You're going to clean it again, and then you you deposit another layer. And then you print the pattern again and repeat just over and over and over. And back to my comment on how small these things are, you can't have any defects on these wafers. The defect can cause the chip not to work. The chip could work in a way that you won't discover because of the defect. Or you may have a latent defect that shows up, you click the button on your TV, doesn't turn on. So there's a lot of technology. For the audience, when you walk through a wafer fab, at least for me, it's almost a religious experience. You just can't believe humans have invented this stuff. It is. You walk through there, and there's nothing else you can relate to outside of that factory that you can compare. It's the machines are automated. The machines are the size of a small SUV. An average machine may be anywhere from $9 million to $160 million, depending on the application, what you're going to print. And then on top of this, you have just tons of robots, automation. I just can't describe to anyone unless you walk through there and you see the knowledge of so many humans pulled together from around the world, working together to bring a product on time that a customer wants at a profit. And those are key words in semiconductor.
That's so well put, David. I mean, you describe it as a religious experience, and I can totally relate to it. I mean, when you're in the presence of a lot of science and technology, I mean, it's one thing, it's really the accumulation of, all of human understanding in many ways, but it's also sort of the pinnacle of high precision manufacturing, right?
Yes,
I mean, you talk about Six Sigma and, close to no error of margin, but there is no margin for error.
There is no margin. And the key in semiconductor is repeatability, predictability, consistency, discipline. I've seen factories contaminated by the wrong screw in a machine that corroded and ended up scrapping millions of dollars. I've seen machines that had a crack in a pipe, millions of dollars scrap. So I'm not saying these factories run like a gyroscope and never have an issue, but the type of people working in these factories, type of people designing the systems that run these factories, the scientists that invent this stuff. He or she, it's not the effort of one person or one nation. It is the effort, as you mentioned, of hundreds of thousands of humans that have worked together to bring this. And I really do. When you walk through there, you think about God. You think about how is this all possible?
Are you a person of faith?
Yes, deeply.
I want to hear a little bit about your own career. And let me put it this way. You're a person who has come to this country to lead and shepherd this project of incredible importance to us, strategically and otherwise. There is a lot of interest around it, as you probably already have found out and you will go on to.
Yeah.
So think of this as, us interviewing you for, who is this person, right? So can you broadly tell us, David, about the projects you've done in the past? What gives you the confidence that you can set up a high precision, incredibly complex operation in a country that's, of course, now we are sort of beginning to make some mark in manufacturing, but we're not really there in terms of high precision manufacturing on the global stage. What makes you confident that you can do it?
It's going to be a multifaceted answer, but the first, I think a lot of people are selling India short. Japan didn't have factories. Taiwan didn't have factories. China didn't have factories. Malaysia didn't have factories. Germany didn't have factories. Italy, France, England, United, a lot of this came from the United States. So I would say people would need to give India a break. My goodness, name something that the Indian country hasn't done that other people have done. Okay, this is just one more thing. The issue here is historically, India is, it's just a different place to do business in. And I think now the environment is more of a pull. And that's what you want. This is so complex. You probably have 50 or 60 countries supplying materials, machines, people, design, and there's this pull now. So it's a lot different. And there's motivation. Everywhere I've gone, I can't say enough about the Indian government. The meetings I've been they're just, this is so important. And it is a national imperative. And, you say, why did you come here? You could have done a lot of other things, ranching or other semiconductor companies. But when someone said it will be the first in India, I said, I'm in, because I know it can be done. So on the India part, I think that we can pull it off. As far as myself, I am cursed with the need to know. I have such insatiable curiosity. My breadth of interest and stuff it impedes me. One lifetime is not enough to know what I want to know. And when I first started in semiconductors, I didn't even know what that was. And thankfully, my first supervisor, Susan Bowman, a wonderful woman, hired me and took time and trained me. And, semiconductors is about problem solving. It is, you have to have an insatiable curiosity. You have to be able to solve problems. You have to have incredible wherewithal. The work-life balance, I'm going to confess, I'm a big violator of that. I have never worked a day in my life. And I think that's due to semiconductor. It is just so interesting. It has physics, it has chemistry, it has light, it has electrical, it just mechanical. It is everything under the sun, and it fits in my wheelhouse. And early in my career, I don't watch TV. I've never been a TV person. I read books. I have a very extensive library to the point that my wife has taken away my credit card, and I'm not allowed on Amazon anymore. But the amount of knowledge that you have to have in semiconductor is staggering, and it's a lot of training. It's a lot of experience. And so when I started in TI, my knack was problem solving.
TI is Texas Instruments?
Texas Instruments, and that's where I started. I had a degree in chemistry and chemical engineering. Love of my life was drilling for oil. And
like a true Texan.
A true Texan, yes. And that's been fun with Vedanta also, because they have such extensive oil. Right. But I can't get distracted on that. But, and you get in there, and what's great about Texas Instruments, you go as far as you can go. And so if you can solve problems, you get moved. And I had 18 assignments in Texas Instruments.
In a course of how many years?
26 years. Software, design, packaging, test, process, customers, business units, finance.
And Texas Instruments at that point was making chips?
Yes, sir. Chips, laptops. They were in very many different things, but they focused on semiconductor. Then they further focused on analog, is where they are now. I can't say enough about Texas Instruments as the integrity, the ability to execute. That was instrumental in my formation in semiconductor.
Right. And you were based...
Dallas. They moved me to Japan. They moved me to Singapore. They moved me to Italy. So I've always been a person to go where the action is, and it's benefited me because I've met a lot of people in semiconductor, and what's been exciting about this project is just the sheer number of people that have contacted me saying, hey, I want to be part of this.
Nice. So 26 years at Texas Instruments, and then what did you do after that?
So then I went to Global Foundries.
Which is an Intel company.
No, Global Foundries was a spinoff of AMD.
Right.
Okay. And AMD made the decision to go fab light. In our industry, you have companies like Texas Instruments, Intel, where they design the chip and they actually build the chip. Then you have companies that are fabless like Qualcomm, AMD, Apple, where they design the chip and then they contract with a foundry to manufacture that. Global Foundries was such a company. And Global sent me to Dresden, Germany. And I was there for 2 years for the 28 nanometer R&D and launch of 28 nanometer as a product line.
And was there a greenfield new project?
No, that factory was started in the early 90s after the fall of the Berlin Wall, when unification of Germany occurred. And AMD took the bold step to say, I want to tap into the German engineering.
So after Dresden, where did life take you?
So what's really kind of cool about semiconductors is it's very large, but it's a very small cadre of people that know everyone. And whenever there's an opening, you immediately think of who do you want on your team.
It's a global brotherhood of people, or brotherhood, sisterhood of people who feel it when they're walking into a fab, yeah?
Absolutely. And, I won't list all the names, but every company, there's 5 or 6 people that that you've either worked with. There's a lot of career hopping opportunities in semiconductor. And so Greg Lowe, fantastic person, CEO of Wolfspeed right now, he was selected to be the CEO of Freescale. Turnaround. And I was at Dresden at the time, and he calls me up and he says, hey, you want to move back to Texas and either be a zero or a hero? It's 1 letter difference. And he said, come to Freescale. And I remember saying, there's certain companies in the A category, B category, C category. At that time, that company was not in any of those categories.
What is Freescale? Who owned it?
Fantastic companies, mediocre companies in trouble. And Freescale was definitely a company in trouble. And they brought Greg in. And so he calls me up and says, hey, help me turn this around.
And what did they do? They made
chips. Right. They were very heavily automotive and communications and microcontrollers. They were a spin-off of Motorola Semiconductor Systems.
Right.
And so for the next 3 years, we turned Freescale around.
What's the genesis of the word Freescale? It's some kind of a mathematical thing.
No, I worked there for 3 years, and I finally asked.
Right.
And I said, what does Freescale mean? It means climbing the side of a mountain without a rope.
Right.
Without a rope.
Right, freescaling, yes.
And I didn't know, and this just shows how clueless I was working there for 3 years and finally asking, what's Freescale mean? Because I thought it was such a strange name. And then, and the world is so small. Then another person, Greg Lowe, a former TIer, and another great person was the CEO of NXP, Rick Klemmer, decided that he wanted to take over Freescale. And when you have a takeover or a merger like that, they line everybody up against the wall. I'm being very brutal here, and they say, we want you. And I got selected to be the Executive Vice President of Technology and Operations for NXP.
And for the merged entity. So that would be
both companies.
And what is NXP genesis, ownership?
NXP was a spinoff of Philips. And you see a recurring theme here that as semiconductors became more expensive, several things happened. It's a very capital intensive. Like as we mentioned, this factory will be anywhere from $7.5 to $8.5 billion. The latest wafer fabs you see in the news are anywhere from $18 to $26 billion.
Those are the 7 to 4 nanometer
yes,
chips?
Sir. Yeah. And people can't afford that.
Which countries make those? Only Taiwan at this point?
Taiwan and the United States and Korea. And I'm sure there are locations in China that are attempting to do that.
Right. Sorry, I broke your flow. You were talking about the recurring theme where companies spun off their semiconductor divisions.
Yeah, so the companies spun off as IPOs their semiconductor operations. They just became too expensive because semiconductor is on this 18-month cycle of being on the next node. So you go from 65 nanometer, then you're going to be at 45, then 40, then 32, then 28. Then you're going to be on 16, 14. So you see this slope of technology, and each one of those nodes are billions of dollars to develop.
And you also, if you miss you also have to invest in step with the technological progress, right? If you get that investment wrong and the timing wrong, you can lose a lot of money.
You're in big trouble. And back to this problem solving, if you miss the problem or invest too late, or don't have the right technology, or don't have enough capacity because you didn't have the money to buy the machines, you miss the window. And so in semiconductors, back to as each node drops, you get more and more chips per wafer. So I'll make a story up. If these aren't the real numbers, but if a chip on 65 nanometer was $1, on 45 it'd be 70 cents. On 40 nanometer it may be 50 cents. You get to 28, it'd be 35 cents. And you see, because you have more and more chips per wafer. Right. And let's say you spend $100 per wafer and you have more and more chips, the cost per chip drops.
Right.
And so if you're late and I'm on time, my cost is 35 cents. Your cost is $1. You're not going to be selling at the same. You're not going to make the same money that I'm going to make.
But I'm a bit mystified by this crazy arms race to make smaller and smaller. For most applications, right? I mean, there is no advantage to, like in a washing machine, which has a certain form factor, or a television which has a certain form factor. There is no advantage to putting a smaller chip in it, right?
It depends. Each application has its own sweet spot. I mean, if you're going to, again, make a story up, if I buy a washing machine and it has $8 worth of semiconductors and it does the job, okay. But if I have a smart washer, and believe me, this stuff exists. I didn't believe it till my wife showed me. That's connected to the network of your house, right, that tells you the wash is done. Or the better one I saw was a refrigerator that knew what was in it and would order your groceries. And so, that $8 worth of semiconductors now is, I'm making this up, $25. And so, it's all about complexity and simplification. And if you have, 8 chips in there, and I can do it with one in a smaller form factor at a lower cost, net cost, then, it makes sense to go down the node. Not everything has to go down the node.
So it becomes more and more expensive to manufacture smaller and smaller nodes. Sir. But the end product for the B2B buyer of that chip, that actually becomes cheaper and cheaper.
If the chip stays the same.
Right.
Now here's the issue. No one wants to stay the same.
Right.
Everybody wants to glom on new applications, new things. And so that chip may have controlled temperature. Now that chip controls temperature. It controls who has access. It now has connectivity to your LAN in your house. It now talks to the cloud. It may have to drive a camera. And so what that little chip, if you left everything alone, the cost would have gone massively down.
Right. But now its capabilities are
just going off the chart. And that's, you have this cost curve going down, but you have the additions of ability of what a chip needs to do going up. And so the complexity of the chip goes up. And back to, that arms race you're mentioning, you want more chips per wafer. And so what you do, if you have the same number of chips on a wafer, you shrink the transistors. Okay? And so now you have the same area of chip, but it may do 30 times more what it did in a previous node.
This is one thing I've struggled to comprehend. They actually print on a chip of the size of your fingernails. Mm-hmm. They actually print 2 billion transistors.
It's all over the place. It can be in the billions, or I've seen chips so small, probably the size of 4 periods printed on a piece of paper. I mean, they're so small. They're smaller than the flakes of pepper.
And that is a chip, and on that there are transistors that
yes,
are printed.
Sir. Yes, sir.
But those transistors, but you don't print a circuit on a chip.
Yes, you do. So back to my analogy of the map of a city. If you were to lay out Delhi, and I'm discovering Delhi is a lot larger than it appears, because I was on approach yesterday morning, and I was like, gosh, when is the airport going to show up? I mean, you just flew and flew and flew over this massive city. And but if you were to take a map of Delhi and say, okay, and then you were to look at a map of a chip, and you stand back, it would look almost the same. A chip is more regimented and square and rectangulars and stuff, but it's a layout. And so what happens on that layout, you want to either shrink it, and you shrink it and have it do more. So you double the size of it, but you have it do 4 to 8 times more things because you printed the circuits. So what we do, we take the wafer, we print the outline of the chip, the rows, the tops, the edges. Then we come back and we print within that square the circuits. Okay? And within that square of circuits are the billions of transistors that you're going to form. And then you go through all the different layers. Now, the tyranny of numbers. You got billions of transistors, you have to connect them together. And so you take a layer of metal, it's very complex, and you have to connect every transistor into and that's the circuit. And so the
circuit must actually be smaller than the width of the transistors, right?
No, the transistors are the smallest unit.
Okay.
And then the circuit is a composition of all these different, it can be anything from a 4-transistor circuit to a circuit with millions of transistors to do something.
And what is the material that is used to draw the circuits
Oh my goodness! It depends on the node. I'll simplify this. It's something called polysilicon, which is a form of silicon that's not crystalline all the way. And I won't go into the physics and the electrical issues of that. And that is the on-off switch of the transistor. Okay, and then you have to, just like in your house. An electrical cord, you have to have rubber insulator around the cord because you don't want to be shocked or you don't want to short. And so we have to insulate all these transistors, and then we insulate the transistors from, depending on the application, the transistor to the left or to the right, or the transistor on the bottom or the top. So you have insulator levels. But to connect those transistors, now you have to drill a hole to connect each one of these. And, these holes are like little wells, like a water well. Just think of it that way. And you make that well, and then you fill it full of metal, and then you make the next level of transistors, and then you insulate, and then you coat it with metal, insulate, coat it with metal, insulate. In each one of those steps, you have something with the connectors, the vias, from one level to another.
What is the metal that you use?
It depends. It can be anywhere from titanium, tungsten, copper, titanium nitride, the jewelry, the gold that you see on your watch or your jewelry that you say, wow, that looks very nice gold, that's titanium nitride.
So the wafer itself is silicon?
Yes, sir.
And then what other materials, apart from the ones that you just mentioned, goes into an IC?
You have insulator levels, you have protection levels, you have stress levels. If you were to make a sandwich, okay, and you have just a simple sandwich, a top layer of bread, and a bottom layer of bread. Now, what if I came to you and I said, I want you to make 10 layers of bread, and between each one of those is going to be the sandwich. And then I tell you, I want you to cut that. You got a big problem on your hands, right? Because you're not going to cut through those 10 layers of bread. So a very, very simple story, but the issue is you have to design so when you cut the chip or you do these processes, it doesn't break apart. It doesn't have stress in it that it would just peel apart. So there's a lot of physics, a lot of engineering on adhesion, on the mechanical properties of the material, and you're asking what it could be. It can be silicon dioxide. It can be silicon nitride. It can be types of polymers. But the really interesting thing about semiconductors are the chemicals that you use to make it that are not part of the chip. Nitrogen, oxygen, argon, phosphorus, boron, hydrochloric acid, sulfuric acid.
Some of this material, I'm told, needs to be of a kind of purity that does not even exist in India.
Well, I would say probably some of this stuff exists, but it's never been applied.
Right.
Okay? And when in the case of this new factory, you have a new country, a new team, a new everything. I was going through the list. There's like 16 news things that we have to go address. If you have that supplier in India, you're not and they're unproven. I'm not saying they're not capable. They're just not proven yet. So you don't want to build this factory, plug in somebody that's not done it before, and then find out you have a yield problem or a contamination problem.
So you might have to bring in a supplier from overseas.
Yes, sir.
That has experience
right.
working in the industry.
And a lot of these suppliers are motivated to develop domestic sources.
Right.
Okay? because, they get tired of flying this stuff on a 747 or a MD-11 or a 777. And they would prefer to develop that expertise in India. And again, you look at India, 50% of the population is under the age of 28.
That's right.
It has an incredible university system. I mean, the brain power here is just staggering. And so you bring in these suppliers that are based in Korea, Japan, Europe, and, I'm sure the government will do everything they can to ease them in. And I would predict they will develop domestic partners to supply, silicon-grade gases, solids, acids, just you name it.
How many suppliers does a factory like the one
Well,
that you're setting up?
interesting, and don't hold me to it. I read so much I can't always remember where I read it. I think that I saw at the 5 nanometer, 3 nanometer factory being built in Arizona, had 1,000 suppliers, and we probably have around 600, 700. And of that 600, 700, there's probably about 200 that are big chunks of money, capital outlays. And of those, there's probably 35 that are in the hundreds of millions of dollars. And there's probably 3 or 4 that are in the billion range. So those suppliers, and this is what's fascinating, those suppliers have to have technicians, engineers. They're going to want local supply. Right? They're not going to fly in everything. So they want to develop a local ecosystem that feeds them.
Right.
So they'll tap into this brain trust that India has.
Right. And there is a across the spectrum technology transfer, right? Across materials, metals, gases.
Yes.
Right? All of that.
Yes.
That's great. Can we talk a little bit about the Dholera project? Where does it stand? What are the timelines? What have you done already? Like, do you already know what size the building is going to be? Has the building been designed? Has the layout of the building, the factory inside been determined? Or all of that is work that's ahead of you?
So let's just talk about the site itself. I've been there personally twice. Foxconn is responsible for building the factory. And I spent quite a bit of time in Taiwan looking at all that. But I can't say enough about the Dholera team. They're working around the clock trying to figure out how they're going to accommodate this monstrosity. Okay, it's never been done before. So there's a lot of specifications, applications, criteria that have to be met, because if you're going to put a $7.5 million building on a piece of soil, you need to make sure that's the right soil. So we've gone through that. As of today, they're leveling the site.
The work has already started?
Yes, sir.
So the work on the land has begun. You're awaiting the government's decision on whether this project is eligible for the capital subsidies that it is providing. Yeah. How hopeful are you that it'll come through, number one, and how soon do you think it'll come through?
Very hopeful. We've had several meetings with the authorities, and the work's in progress. We're going to follow the process. I would expect that to happen soon.
What have been the sort of top questions or concerns that the committee has asked you in the course of reviewing this project?
Well, it's very important, and I understand the level of questioning and scrutiny, because it is a effort using public money, and you have it doesn't exist in India. We have 2 fantastic companies. We have one company, Foxconn, $220 billion a year revenue. Foxconn purchases over $60 billion of electronic components. I mean, I may have the wrong number, 1.3 million employees located all over the world. Just the breadth and depth of this partner is staggering. And then on the other side, you have Vedanta, which is a very great company, and it's very heavily invested in what I would say extraction, metals, oil, and gas. And I can't say enough about the chairman and the management team. They're all in. They do have experience with technology. I mean, if you look at fiber optics, you look at the LCD panels, displays, this is not something, it's new, but it's not something unfamiliar. But that said, it's semiconductor, and that's a whole different level.
So even Foxconn does not make semiconductors?
Yeah, yes, they do. They have several small wafer fabs that are specialty fabs, but they don't have a 300 millimeter mega high volume fab. But, they have hired hundreds of engineers. I've personally met with them. Can't say enough about Elong and Dr. Bob Chin.
Sorry, they have hired engineers for this project
Yes.
already?
Yes.
Wow. Okay.
Yes.
Okay.
And, Foxconn is responsible for bringing the factory, providing the technology, doing the transfer.
And they also have about 37% of equity in the
Yes,
project.
it's a 63-37 JV.
So that's the capital they will bring in.
Yes. Well, they're still working on the capital, but the other reason I mentioned that, you also now have the government funding, which will match what the JV puts in.
Right.
And so it's due diligence. I mean, the government's doing the right thing. They're asking the questions.
Right. So in this process, what had happened was the government first invited expressions of interest, and there was a 45-day window, after which they closed the window, and there were about, I think, 3 or 4 candidates in the running. Now, it was reported yesterday that the government is opening that window again.
Sure.
It is, it's open to interpretation, but certainly one interpretation could be that it stems, or the decision has been prompted by a sort of lack of confidence in the existing candidates?
I disagree with that. No, I mean, this is a flywheel effect. And the first person that goes in, there's going to be a number 2, number 3, number 4. And I think what is happening is now that they see the success of the Vedanta-Foxconn effort, they see this thing coming together. They see us hiring world-class talent. They see Foxconn hiring all these people. I can't go into the details of the technology. We've secured manufacturing-grade technology. So people see this coming together, and we would welcome other companies coming to India. Back to my comment of the more semiconductor that resides in India, the more the pull will be for the suppliers to actually locate here in India and not support us from Japan, Korea, U.S., or Singapore or Europe. So this mass of this gravitas of wafer processing, you want. You don't want to set this off to the side and say, okay, only these guys are going to do it. I welcome these other applicants to come in because it helps all of us.
Right.
A rising tide raises all ships.
Absolutely. And an ecosystem is really critical.
Ecosystem.
Having said that, I mean, another sort of hurdle perhaps at the moment, I mean, as an observer of the project and everything that's going on, another question mark is around the financial headwinds being faced by one of your parents, Vedanta, around the refinancing of some of their debt and all of that. Do you think that creates a perception issue for the project ahead of the government subsidy approval?
Be very open to you. I've been so focused on this project, on the infrastructure, the technology, hiring the people. I have not even spent 1 second on the stories around that. I can tell you this, that Vedanta and the chairman and the Foxconn chairman are all in. I have no doubt that the funding will be there. I have no doubt the commitment of these two companies. There's noise around this, and it's just lack of information or timing of the information. Right now, the key thing is to get the government approval for the government investment, because it's very expensive, and people may ask, well, how can you do this? Well, the problem is there's no infrastructure, so you have to build that infrastructure. And on top of that, you have to build the factory. And on top of that, you have to buy the technology. On top of that, you have to go get the people. On top of that, you have to have a social ecosystem around this to attract the world's best talent. So, there's a lot of moving parts to it, but I have no doubt that these two mothers and fathers are going to make this happen.
And the returns on this investment happens over a long period of time, right?
This is going to take... We will have the first shovel in the ground ceremony this fall, October, November.
Very exciting.
Very exciting. Mm-hmm. It's all hands on deck. We are hiring the best we can worldwide.
How many people will you be hiring for this project?
Once the factory's up and running, probably around, I say a low number is 1,300, and then depending on what else we're going to be doing, could be approaching 2,000 people. And then, we'll have 1,500 people on the site this year for construction, and that will climb to over 3,500 people next year, construction. So it's not, while the government is going through their process, which they should do, as any other government would do, we're going full speed ahead, 100 miles an hour. And we're working with suppliers. We're working with the technology suppliers. We've already started talking to potential customers. So, just the amount of interest on this has been incredible.
So you already have a team that's sort of negotiating with suppliers, tying up those contracts, figuring out logistics. All of that work is already on.
Yes, the Foxconn team, back to these 200-plus people, there's a procurement team, there's an engineering team, there's a finance team, so they're all working that right now.
There is a 200-plus person team at Foxconn.
I don't know the exact number, but there are a lot of engineers working on this project.
Have you met all of them?
No, I plan to.
Right.
But Dr. Bob Chen and my partner at Foxconn, Elong, have done an incredible job attracting talent for this project.
Right. Tell us more about the timelines, David. So, first shovel in the ground in October. When does the construction finish?
Immediately. Let's say the end goal, and this is what counts. People need to count. Remember, we have to supply a product a customer wants on time at a profit. And our objective is to have the first revenue wafer in the first half of 2027. So you can work backwards. I mean, as the next 22 months, once that shovel hits the ground, it is all hands on deck for 22 months to build the shell, build the utilities, build the infrastructure, have the equipment arrive, build the interior. And, back to your comment, the contamination, are the suppliers all qualified? And it is going to be a cast of thousands of people.
My head is spinning just considering the amount of work ahead of you, David.
But it's doable. It's been done. I mean, there's over 50 factories under construction right now worldwide. Every day you see an announcement of an extension or a new factory. So, and we're not doing anything inventive here. And this is key. These two nodes, the 40 nanometer and the 28, are volume nodes. And that's where we want to be. We want to do volume. We don't want to spend all this money and then have a few thousand wafers come out. We want 40,000 wafers shipped every month for revenue by, it'll take us from 2027 to 2029 to ramp up the factory.
And for, say, from 27, when the first wafer comes out, for another 10 years, right, you're confident that that size of node 28 will remain in demand and in use?
Absolutely. There's different trends going on now. Back to our earlier conversation, if you were to go on a 5 nanometer part, you're looking at one design anywhere from $250 to $500 million. One design. That's just the design. We're not talking about the printing. We're not talking about the wafers. So, on some of these products on an advanced node, you're looking at $750 to $900 million just for one product.
And just on the design of it?
The design in the prototypes and verification of the design.
And the design is what you pay ARM?
There's all kinds of third party. ARM is one of many out there. But, you would spend easily $250 million of your own money on your own designers using third-party software, third-party IP, your own IP. And so, that's rarefied atmospheric physics, okay? Not everybody's going to do that. And so the mainstream, back to my comment, will be the 28 and the 40. Take automotive. The volume node for automotive just 2 years ago was 55 nanometer, and now they're converting to 40. So 40 has a long ways to go for automotive as a supply. And then there will be 28 after that,
right.
Okay?
And so you're making both 40 and 28?
Yes, sir, in parallel.
Right.
And for the audience, you install the 40, you spend all that money on the 40, anywhere from 70 to 85% of that 40 is reusable on the 28. So it's not like you're spending twice, right? There's only 13 types of machines difference between 40 nanometer and 28. They're very expensive,
right.
But that's better. 13 is better than hundreds.
Right. And David, tell us a little bit about the benefits of having a fab to a country and its electronics manufacturing and other manufacturing ecosystems. One question that has emerged, of course, after the pandemic is the question of self-reliance. If there are supply chain disruption, etc., you don't want to be dependent on others, and you have secure supply. But there is also a question of cost. Does the cost of final sort of electronics that we buy from the market, is that going to come down because we make chips here in India?
Well, there's different things at play here. We'll peel the onion. So, number one, the pandemic or epidemic, exposed that any particular country with a tweet could stop everything. Now, I'm overemphasizing the tweet part, but someone could snap their finger and say, nobody leaves a building.
Correct.
Well, you have a $15-20 billion factory sitting there idle. What do? Okay? And so that having a supply that's predictable and is, in terms of secure, that when you place an order, it's going to provide you wafers. That's one aspect of it. So the companies recognize just how complex the semiconductor food chain was. United States locked down, Japan locked down, Korea, everybody locked down. And depending on what factory was sitting in which country, it just all went crazy. You can see that in the automotive market. So there's that aspect of it. So you want to have more lines of supply. The other thing that's going on is if you look at the semiconductor market, the content, the cost of the components are dropping, but what each component does is increasing. So not, if you bought a mobile phone for $10 today, and I'm making that up, and, through technology you think it's going to be $5, you're wishful thinking. That phone's going to do 20 more things. It's going to cost twice as much. So there's that aspect of it. So the semiconductor market will almost hit $1 trillion by 2030. So, it's at 600, 700 now, going to $1 trillion. So the first part was secure my supply line. The second thing is I need more capacity. And then the third leg is the geopolitical. You could wake up one day and find out the world's upside down. And so customers are going, where else can I go? And so the answer is India, India, India for all three of those situations.
Right. David, when we talk to people in the ecosystem, look, I mean, this is not, as you probably know, this is not the first time that India has embarked on this project of trying to set up a fab. I think back in 2008, as far as, dating as far back as 2008, there have been projects. There have been projects there have been talk of various kinds of government subsidy and so on. It's been an ongoing project for a long time. Hasn't really materialized so far. And partly because of that, and partly, I suppose, because of the overall complexity, there is a lot of skepticism around this round of India building fabs kind of scenario, where people, genuine technologists, who believe it's not going to happen. People are like, okay, we might be able to build a packaging facility, making fabs, not going to happen. Is this skepticism natural? Have you encountered it in the other projects that you've involved
we
with?
welcome the skepticism. You're only as strong as your
worst critics.
Yes, I mean,
Right.
they make you think.
Right.
And I'm okay with that. And they're bringing up valid points, but it is India's time. The government's behind it. The people are behind it. The JV's behind it. Foxconn's behind it. Vedanta's behind it. The suppliers are behind it. Customers are behind it. So I think you have a much more positive dynamic that, is this going to be easy? Absolutely not. Is it doable? Absolutely yes.
How many hours a day do you plan on working all the way till 2027?
Personally?
Yes.
Oh, gosh. There is no work life. Typical work week, 80 hours probably or more. But like I said, I've never had a day of work in my life.
Because you enjoy it so much.
You just cannot describe the feeling when you get a team together with the right culture that's executing in unison for a common goal. It is just phenomenal. And, on this note, I'm a big, big proponent of diversity. And I want to make sure everyone knows that everyone will be welcome to apply to this endeavor. And so, I've been, having, 50% of the women graduates. I mean, they need to be applying. So we're going to make a real effort on diversity on this. But, there's a time and place. I don't care if the person's blue. If they have the right expertise and they live in Venezuela or Brazil, come on board. But at some point, this has to be an all-Indian entity. But the key point is this thing needs to execute like a semiconductor company. It doesn't need to execute like an American company or an Indian company or a Korean company. It needs to be a world-class machine executing as a semiconductor foundry, a trusted foundry that we will not compete with our customers. We will be the benchmark supplier from India.
Three most important things to be watchful of for a facility like the one that you're building. You have to be very careful about dust, of course, like the company dust. The water has to be hyper pure, and the terrain has to be stable without much traffic around and all of that. Is that how it works?
Yes.
Can you talk to us a little bit about all
one
three?
of the key things here, if you're going to put a $7.5 billion building up somewhere and you're printing, okay, let's think about this. You're printing the transistor to the width of a red blood cell. That building can't move. That building can't vibrate, okay? And, if the water table changes the consistency of the soil, or if you decide to add super heavy machines on a certain floor, it can't vibrate. So this is one of the things we've been working with Delera is this earth fill. They have to put in, 3 or 4 meters of special soil, which they're doing now, we're attempting to do now. And then once we have the soil, then you have to drive these pile drivings way down into the earth, the hold the building firmly to the earth. So I say the key points will be, you'll see the earth fill, you'll see the floor of the building, the basement, and then when you see the four walls, but a key thing will be the roof. When you see the roof goes up, it's well on its way.
One of my favorite business stories from recent times was the New York Times story about ASML, the Dutch company that makes, that's the only company in the world that makes the machines,
that prints the circuit. Yes.
Right. Tell us a little bit about ASML. Why is it that there is only one company that's able to do that?
I have worked personally hundreds of hours with ASML on 28 nanometer, and it is absolutely back to the religious experience. The physics involved is staggering in the precision, the accuracy, the repeatability. And I'm not talking about printing one wafer an hour. I'm talking printing 60, 80, or 120 wafers an hour. This thing looks like a printing press, but you're printing, transistors, the size of a red blood cell. Just work with me on that for a minute. And so you integrate that. And so there's three really key companies: Nikon, Canon, ASML. And this relentless race of having the lowest cost, most...
Sorry, which are the three?
The three lithography companies are Canon.
Canon, the photography company?
Yes, sir.
Really? Okay.
Nikon.
Again?
Yes.
Cameras?
Yes. Well, the printing...
Right.
Think of the old film emulsion technology on the old film. That's basically how we print a wafer. We coat it with a very photosensitive coating, and we inject the light with a pattern. And so Nikon and Canon went into this business, very capable companies, but it's a horse race. And ASML did the investment, and they're benefiting from that now.
And they only make about 6 machines a year.
No, I can't go into details. I don't know the latest numbers, but they build hundreds of machines a year of different models.
Right. Maybe the elite ones, they only build very few. And
I stay away from EUV because that's so expensive. But I'm just going.
What is EUV?
Excimer laser-based ultraviolet X-ray. Basically, it's a soft X-ray. It's a soft X-ray type of deep, extreme deep UV light. The machine is about the size of a bus, anywhere from $160 to $200 million. So I don't want to be dealing with that. I'll let the professionals deal with that.
Right. David, it's been really wonderful listening to you. It's been most instructive. I learned a lot in the course of this conversation. Thank you for joining us today. Welcome to India, and all the very best for your project.
And you've been an exceptional host, and thank you. And I really want to thank the people of India. I can't say enough. I will leave with this: perception does not match reality. And I tell everyone this because when they said, I'm taking this role, and everybody's like, wow, this is like the Saturn moon rocket, And I said, yeah, this is fantastic. They go, but it's India. I go, so what? You guys, you need to understand India. And I think more people need to come over here. And this project will be successful.
You've been pleasantly surprised so far.
Yes, very, very surprised. I'm not surprised. It's just been great.
That was my conversation with David Reed, CEO of Vedanta-Foxconn Semiconductors. He will be a closely watched figure in India's journey to becoming a semiconductor manufacturer. I hope you enjoyed watching this episode of The Sketch. For more such videos and business insights, follow Mint on YouTube. For more podcast content, follow HT Smartcast on YouTube. Thank you for watching.